Hector, as Yannet said. So I know some of you were given the homework assignment of reading the paper, and to your relief, this is the engineering version of the talk. And what we write in the paper and what we actually do are related, but tend to be very different, because you'll find that when you have to deploy stuff in production, the scale of the data is much larger than small data sets that we can play with in memory. So this is a very practical talk. It's how we actually do some of the stuff as opposed to what we would like, which is what ends up in conferences like ICML and NIPS. So just a show of hands, how many of you know how recommendation engines work? Okay, so 50%, great. Just to cover the other 50%, I'm going to cover some basics. Usually people recommend stuff to you on Amazon or like a shopping center by looking at two kinds of similarity. You can look at item-based similarity, like you bought some bread, you probably want to buy some milk, You can also go by user-based similarity, like demographics, This is a working class person who has a family of 10, and this another mother comes in with another family of 10, probably buy similar stuff like diapers or something like that. So what the first one does, the item-based similarity, the simplest thing we can do is compute some similarity matrix between items. And the simplest thing you can do is just count, right? If 100 people all buy milk and bread together, then they're probably good to recommend together. But there are some problems with that. Like, for example, I don't know if you guys know what Gangnam Style is. Anybody? So Gangnam Style is this super popular K-pop music video. It's worth watching once. That went viral on the internet and everybody loved it. But the problem with that is it co-occurred with almost every video in existence because everybody wanted to see it. So if you watch some obscure video about soccer, suddenly you get recommended the Gangnam Style. And why? Is because they co-occurred a lot. So that's one downfall of just naive techniques that just do simple counting. You have to be smart about how you count. And one possible way is to compute mutual information or Dice correlation coefficient. But even those have some problems. Like they'll still co-occur a lot if a significant fraction of the co-occurrences happen with the popular item. So there's some downside with just using counting methods. The other downside is you don't know the user's overall interests. You know just one interest they have. Like suppose the person bought a lot of bread and you can recommend milk, but what happens if bread is just one item and the basket actually contains a lot of books on science or something, and if they happen to want more books, then your algorithm will recommend milk for no reason. So you want to consider all the users' full interests instead of just one item at a time. So this is what I said before, the counting methods. One way to do it is you count the number of times bread and milk co-occur, divided by the number of times bread occurs and milk occurs, and then you get a score. And then you can just make a table of, for every item, what are the top scoring other items to recommend. But like I said, it's just item by item. It doesn't take into account the user's overall interest. So the other way to do things is to do a vector-based method. So what I mean by a vector-based method is your items are just points in space. So things like bread and milk, they should go together, and then they should be closer together than something that they haven't seen. In this example, how many people know what Lady Gaga is? One or two? Well, it's like some popular singer that has two songs called Bad Romance and Poker Face. So usually a lot of people that watch Lady Gaga will watch both together at some point in their time. So you want to optimize your model so that the dot product between Bad Romance and Poker Face better than like Bad Romance and Friday, 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 which is also a very popular internet song by, forgot who it was, some lady whose parents paid for the movie. Also a very popular YouTube star, but they should not be as similar because they don't co-occur together as much as Lady Gaga's two songs. So then you want to optimize such that the similarity between Bad Romance and Poker Face, which is this dot product here, should be more than the similarity between Bad Romance and some other song plus a margin. And the margin you can pick to be any constant, and usually we pick it to be 1 because when we take the derivative, it goes away anyway. How many people know calculus? I hope everybody? Okay, good. Because like in the calculus, d constant by dx just vanishes, so it doesn't really matter what margin you want, you can tune it, you just pick 1. There are many ways to solve vector-based models. How many people know what singular value decomposition is? Okay, everybody, great. So the simplest method to do vector-based models is model the user matrix, right? Everybody's familiar with that, won an extra prize. But there are some problems with it. One problem is optimizing the wrong metric. You don't really care how well you reconstruct the matrix using the L2 reconstruction error. Because when you do that, the matrix is mostly zeros and then ones here and there, right? If you optimize for the L2 reconstruction error, what happens is you try to fix all the zeros to be 0, and then you don't spend as much attention on the ones, which are the watches. So on the other hand, the Wsabie algorithm optimizes so that the rank of the watch items are higher than the rank of the non-watch items. So what does that mean? Like, if you watch something, you want that to be higher in the list in your top K than something you didn't watch. And ordering matters when you do retrieval on search. You want, because the user on YouTube only sees like maybe the top 20 videos out of a corpus of billions of videos, right? So it matters a lot where the video ends up in the list. And you want to make sure that the top of your list is more correct than any other location in the list. And that kind of metric is called precision at K, where K is like the cutoff. In this case, it's like 20 because you can only see a finite number of videos at a time. Again, like I said, you want to optimize so that your two watch items are more similar than something you watched and something you didn't want to watch plus some arbitrary margin. And the way you set it up is to set up a loss function. How many of you are familiar with loss functions? Okay, so a loss function is some mathematical object that you use as a proxy to represent what you actually want. It actually doesn't model completely what you actually want, but it's a good approximation. Like maybe what you want is the number of corrects, which is 1, is better than the number of mistakes, which is 0. But that's like a step function. That's called like a 0-1 loss. And with a step function, there's no derivatives on the left and no derivatives on the right, and a delta function there. So it's very hard to compute derivatives because the derivative is 0, infinity, 0. So you can't really solve it. So you approximate it with, in this case, hinge loss. Hinge loss looks like this. So the gradient is 0 if you're correct, and a smooth linear function if you're wrong. So the algorithm can walk down to the minimum in a smooth manner. You're replacing all your ugly step functions with a ramp. And you can drive your stochastic gradient descent down the ramp. So for those people who think visually or tactile manner, what this algorithm does is on the left you have Poker Face, and on the right another Lady Gaga song called Applause. They start out randomly in space. You scatter these videos out in some 64-dimensional latent space. 64, I'll explain that number soon. And so they start out all over the place. And then you pick a user. And the user has watched Poker Face and Applause. And then you compute the distance between those two and the distance between Poker Face and Friday, Friday, Friday. If Friday, Friday, Friday is closer than Poker Face than Applause, you bring Applause closer together, and then you push Friday, Friday, Friday further apart. And if it's correct already, then you just do nothing. That's the nature of the hinge loss. Because on the right-hand side of the hinge loss, the loss is 0 if you're correct. So why the 64-bit factor? Well, when you do SVD, it tells you the number of modes of your sparse matrix, right? It also tells you the amount of variance explained. And so you can run SVD first to see how many modes explain how much variance. And people pick some arbitrary threshold like 90%. Like 90% of the variance of my matrix is captured using like 40 factors. And that's what people at either Pandora or Spotify did. They found for music about 30 to 40 factors are enough to explain most of the behavior of what people watch. I use 64 because I'm an engineer, and computers like powers of 2. If you happen to pack everything in one cache line, it just runs faster because the vector code likes chunks of 16 size floats. And so I know what I'm using in the back end is an Intel chip, and Intel chips like to do 4 floats at once, so I make sure that I have powers of 2 to fit the cache line and to optimize for the vector arithmetic behind the scenes. A lot of the researchers have 10 fingers, so they like powers of 10. Usually they'll pick 100, which is nice for papers, but then you find you have a lot of leftover odd number things that don't fit in cache lines and vector registers. So if you're dealing with computers, just keep that in mind. Computers like powers of 2. So. The other thing I just didn't mention was weighted ALS. That's the other popular algorithm in Mahout. How many people know what Mahout and MLlib are? They are the open source machine learning things that run on Hadoop and Spark respectively. They do have some weighted ALS algorithm built in. And the difference between that class of algorithm and Wsabie is that they contain 2 matrices. One is the user factors, and one is the item factors. And so for billions of users, you have a billion dimensional by 64 user matrix, and then another billion dimensional by 64 item matrix if you have billions of items. And you can see you have like 2 copies of the matrices around, and that is like twice as much space, right? So for some scalability reasons, we drop the user factors and we treat them as a user as a bag of what we've watched. So instead of having one explicit user vector per user, we just say, okay, the user is the sum of the videos they've watched. And then we solve it that way. So that way we don't really need to keep the user factors around. So now that we have our fancy model, the first thing we did is, okay, let's just try and score the whole corpus, see how long it takes. At Google, we have many, many thousands of machines, so I figured, oh, we just throw computers at it and we get an answer. So we tried it, and we have billions of users and many, many billions of videos. And for every user, we have to score the whole corpus of billions of videos to find the top K to show it to them. And then when you do brute force, it's like 10 to the power 9 times 10 to the power 9, and it took a week and never finished. So okay, back to the drawing board. Brute force doesn't work. So how many of you know how to cluster objects? Familiar with clustering? Not so many. So clustering is a form of unsupervised learning. You try to group stuff together, and there are many ways to do that. You can do locality sensitive hashing. Anybody knows what it is? Not that many. Oh, okay, 1 or 2. I'll explain that later on. K-means, how many people know what K-means is? Okay, so just to go through each of these algorithms, clustering in general just splits your stuff up in a space so that similar things go together. If you split it up 10,000 times, then you get a 10,000 times speed up. And graphically, this is what it looks like. The first one called locality sensitive hashing. There are many variants of it. LSH is just the lookup table part. How you generate the hash codes is another. And one way to generate hash codes, I'm not very much a fan of because it doesn't work too well, but it's very easy to do, is to just do random projection. So let's say this is your cloud of items. You take a random number generator seed, you generate a Gaussian from it for every dimension. You multiply that with your your dimension, and then you get out a single value, right? Which is which side of the splitting plane it is. So locality sensitive hash just splits up your point cloud into a bunch of random splitting planes, but make sure your random number is consistent. So you get a consistent hash for something that occurs like here. If something that occurs here, it has a 1 for the blue side and a 0 for the red side, so the hash code will be 1, 0. And if you keep on splitting up and you get 10 hash bits, then in effect you're splitting up your point cloud into 1,024 different split planes. So that's one way to do it. Another way to do it is to do k-means clustering. You initialize your points randomly, like 1,000 points. You just pick them from your point cloud. And then for everyone, you find the nearest neighbors. And then anything that lies closest to that point, you average it together. And eventually you converge into this equal size spheres around your items. But for our case, we train the objective function to be a dot product, right? Dot product and Euclidean distance are two very, very different distance metrics. So the behavior is not quite what we want. So the other way to do it is to do clustering in cosine space. So you don't want to use your vanilla k-means clustering using Euclidean metric because that's not what it was optimized for. So instead, you can replace Euclidean distance with cosine distance, and what you get is this bunch of cones of where your items are clustered. And actually, we did a visualization in 3D of the 64-dimensional space the YouTube videos lie in, and we projected with PCA onto 3 dimensions to see what it looked like. And it turns out to be like an ice cream cone. A lot of the popular videos were on the shell of the cone because we kept the norm to like 1. And the reason why we discovered after the fact, observing the data, is because the longer your vector is, the more likely it is to match the dot product with any other thing, right? So it turns out that the magnitude of the vector actually captures the popularity of the video, which you can't really get in Euclidean space. So in hindsight, after visualizing the data, we found out, wow, this dot product space is actually pretty powerful. It captures popularity as the magnitude of vector, and the angle is like where the interest lies. So that tells you it's just super important if you're a visual person to visualize your data. You'll find funny bugs that way. You would just have a better understanding of what's going on underneath the hood. So I highly recommend that you always visualize your data if you can. So what does it look like? So we did ImageNet is this popular image corpus that academics have labeled. It's like 9 million images and 16,000 labels. It's a nice small toy data set we can play with to see how the algorithms work. And so the Wsabie baseline, of course, there's no speed up. And precision 1 is like, what's the probability of us getting the first image correct out of the corpus of 9 million? We score all of them. What's the probability of getting the right label, right? So the baseline is 8%, it's not bad. And the question is, do we lose performance? And it turns out, yes, we lose precision performance because we're doing an approximation technique with this clustering, but we get a huge speed up. So what we do is we take, in this case, it's an image feature. We project it down into the Wsabie space, 64 dimensions, and then we compute the dot product with all that projection, all the label vectors. And the brute force way, I have 16,000 vectors. I project my image down to that space and compute dot products and find the best one. With the k-means method, I find which cluster the image ended up in and only score the top scoring images in that cluster. So with 1,024 centroids, you get 1,000 times speed up, but it's not really 1,000 because of overhead. HK-means is hierarchical k-means. With k-means, it's slow because you still have to figure out which of the 1,000 centroids you're in before you score. Hierarchical k-means splits up clusters in like 2 by 2 by 2. So at the top level, you get 2 children, and then another 2 children. So you actually score only 10 centroids before you finally leave. So it's much, much faster. And LSH I covered earlier. It's fast, but then you get much, much worse performance probably because of the random projection way of computing the bits. There's some problems with using the mean of the user. Like I said, we use implicit user factors, so that means a user is sum of the vectors of what they watch, right? That usually works if you watch only one kind of video on the internet. But let's say you like cat videos too. So let's say I like pop music and cat videos, and everybody likes cat or dog videos, right? So what does it mean if Lady Gaga songs are here and cat videos are here? I average it, it's over here, and what does that mean? Like, where is it? And so a lot of bugs came up because of that. People are complaining to me personally, it's like, why are you showing me like Google Chrome videos all the time? I have other interests. And it's sort of like bad user experience, right? So what you can do is, instead of treating the user as just the center of the point cloud, the user has many, many different interests. Why not give the machine learning algorithm a flashlight? So let's say it's walking around in the dark, and each video has a flashlight, and they shine it at the user, and they only see the nearest part of the user. So if I'm the user and the video is over here and my hand's over here, he only sees my hand, it doesn't see my whole body. So in effect, it only captures the local interest of the user closest to the video. And that kind of method is called density estimation, or kernel density estimation. So you put a kernel, and in this case, it could be like a radial basis Gaussian around a video. It's like a smooth bell-shaped thing, right? And then you weight all the points of the user from the distance to that bell curve. And then only stuff nearby you score. And that gives you a multimodal representation of the user. And the user is no longer the average of all the points, but a weighted sum of stuff that's near the video. It's a lot more expensive to score, but you can do it in combination with the previous techniques to get a retrieval set and then do this. And what you get is you can capture more than one mode of the user's interest. And this paper is called Affinity Weighted Embedding, and it's in ICML this year, I think. So that's the end of my talk. I left a lot of time for Q&A. Some funny, interesting things that we found. There are many metrics to use when evaluating the offline metrics of the model, and we found precision at K didn't correlate that well to a metric launch. In our case, our metric was how long people watched videos on YouTube, and in addition to how many videos they click through. And we found that mean rank performs better, correlates better with this metric than precision at K. Probably because a user has more than one interest, and you want to capture the minority interest as well as the majority interest. So the mean rank captures this better. And another interesting thing is if we just threw machine learning at a problem and just sorted videos by the same machine learning score, it didn't do so well. Like initially you get a big spike of lots of watches, and then it trails off, and then it's like, well, what's going on? We're showing them the best possible video we can think of. And the problem is exploration versus exploitation. The users don't know, they might or might not like things they haven't seen. So you have to turn up stuff, novel stuff for them to see, so they can decide whether they really like something or not like something. So one easy fix is to just add a small random number. It tends to break ties between algorithms that give a discrete score, like random forest or boosting. Those have like score buckets that are very, very discrete jumps. So if you add a small random number about the size of the jumps in scores, that shuffles up the distribution of what they see. And that also models the uncertainty. If you're coming from the generative model world and you have a very nice concept of uncertainty, you have your maximum likelihood answer and then the uncertainty around it. a lot of the discriminative machine learning that we use don't provide uncertainty, but it turns out to be a good thing to model, because then it models naturally the things you don't know about. And you just add a random number about the size of the uncertainty, and that fixes it. That's it. Any questions? Sure.
Yeah, you talked on the earlier slides, you talked about watched and unwatched, and what's the margin. Can you expand a little bit more about the margin that you're using, or at least as an example?
What the margin is?
Well, what would you use as a margin?
Like I said earlier, it doesn't really matter. You have to tune it. It's like a parameter, hyperparameter that you have to tune. You can try like 0.1, 1. It really depends on your problem. It's just like how clean a separation do you want between things that you've seen and things that you don't want to see. If you set it to too high a value, that might be bad, because it might, for your negative, you might be picking something you like, but because you haven't seen it yet, you don't want to push it too far away, right? We assume everything you push away is bad, but it might not necessarily be bad. It might just be something you don't know about. Like, there were entire classes of videos that I didn't know about, that eventually when I got around to seeing them, they were very funny and I did like. But because we're using implicit feedback, we assume things you don't see are bad, but they're not necessarily bad. In that case, you want a small margin. But if you have very clean data, for example, labeled data from raters or something, then you can afford to set a higher margin, because you know something like a spam or something. Like spam or malware is bad, it's definitely bad, then you want a high margin. It's the same as the SPM margin. It's like how far do you want the separating plane between your classes to be.
So when you talk about Lady Gaga's combined,
like this one?
Yeah.
In this case, because Friday might be in the pop music sphere, you don't want to push it too far away. People who watch Lady Gaga might actually like Friday. So you will pick a smaller margin. Especially when it comes to entertainment, you can't model user behavior that well. You don't want to push a similar pop music video too far away. So you pick a smaller margin. But the only way to find out is to run multiple hyperparameter searches, compute the metrics of a holdout set, and whichever best optimizes the holdout set metric that you trust the most, you try launching it and see if it works on live humans. Again, like I said, these losses are proxy losses. They kind of approximate what is actually happening. But what's happening sometimes have interactions beyond your control. Like, maybe it's a UI. The UI impacts click-through rates a lot. So it could be a UI problem. You don't know. So you have to try multiple experiments, and usually you want to pick 3 because they tell you the direction you want to go. Like you could be an inflection point. Yeah.
That would require your margin.
You could try like margin 0.1, 1.5. There are other hyperparameters to work with too, like learning rates, how you select your negatives. Like this negative, I didn't say how to select it, right? If you pick a random negative, you end up optimizing for area under the curve of the ROC curve. But that's not what you want, because I don't care if the middle point is negative. I care if it's a bad video at the top of my ranked list. So then there are other loss functions like weighted approximate rank loss, where you repeatedly sample the negative space until you find a margin violator. And then the number of samples you've done, you take a harmonically decreasing series, like 1/i or something, and that's a weight you use. So if you pick the first example, it violates a margin, you set it to a weight of 1, and update the gradients with that. But if, let's say, you have a corpus of 1 million videos, and the last one you pick is the violator, then you know you're pretty close to a solution. So you probably don't want to move your model that much. You just move it a little bit. In this case, you move it 1/99999. Move it a little bit because you know you're correcting something that's already pretty close to convergence. The other algorithms that are popular are ADAGRAD, adaptive gradient descent. And that one you take 1 over the square root of the sum of square gradients. That also makes it slow down convergence. In the beginning, it takes a full step, but as the feature gets updated a lot, it slows down. So there are many, many ways, hyperparameters to do, like what training algorithm. You can use resilient backpropagation. One common way to do it is Gaussian process models to tune your hyperparameters, but lately people have found just sampling randomly seems to work the best. So you use this random learning rate, use this random margin, use this random training algorithm, and just pick the best one. And that works best because we humans don't know how the hyperparameters interact. And it's just, for some complicated decision space like that, you might as well just randomly sample. A lot of smoothness assumptions that come with Gaussian process models might not hold because the way you change a hyperparameter from one training algorithm to another is not smooth, right? It's like it could be huge jumps in performance just on one discrete choice. Janet, you have a question?
I have a question about just how you set up the model itself. So do you use like how many times a user have watched a video, or for how long, and what period of time do you use? Like, do you use last month, or do you use like the whole history of the user? Like, and also how you take this freshness into account. Like, okay, there are a few questions. So
Yeah.
I'll leave you there.
So that depends on what you want to emphasize.
Mm-hmm.
Like we tend to just do the unique views because some people might have videos on playlists or auto playlists. Let's say they like going jogging in the morning and listen to the same playlist again and again. You probably don't want to recommend that again because they already know about it. So it's probably better for recommendations to take a unique set rather than weighted by views. And it's very important in recommendations, particularly to do lots of exploration. People seldom ever want to watch something they've seen before. And if they have, they probably already have bookmarked it or know how to search for it. So people come to YouTube for novelty. And in that case, we would take the distinct set of watch videos rather than weighted by view count. In terms of like freshness, you can decide I only want to train on the last K videos the users have watched and just drop the rest. And then for the rest, you might at serving time decide, okay, let's remove everything the user has seen so they only see new stuff. So that's more like above the level of machine learning. It's how you use the machinery. I think those are the two questions you asked, right?
Yeah, possibly.
Yeah.
You said that you add in some random magic just so that people see things that they might not have seen before. Do you ever take into account like details about the user for that, so demographics, or this has nothing to do with demographics, right? It's just about
the strongest signal we've seen from the user comes from what they've watched. So coarser things like demographics lead to a lot of bugs. Like if you notice on Google Plus, I had a lot of my female friends who are in tech complain. It's like, why does Google Plus always show me all these feel-good articles? It's like cats and everything. I also want to see tech news, and why am I not getting it? And the reason is these coarse modeling things don't model you, right? I mean, 50% of the world is female, 50% is male. I'm not like the 50% of the whole planet. Just sex is too coarse a demographic bin. Even sex cross age is too coarse, right? I'm not like all other males between age 25 and 50, right? The most specific thing you can know about the user, or at least by computers, is their user ID, if they have a cookie or something. And then after that is like what they've consumed, like whatever you've watched. That's a much, much stronger and fine-grained signal to the machine learning than any kind of bucket thing. The bucket thing is a good fallback. It's like, okay, I don't know anything about this user. Let's fall back on some kind of demographic bucket. But that's the worst possible signal you can use for active users. You probably want to use it as a cold start thing. And then after that, like, it's kind of like if you're familiar with the Bayes equation, if you're prior, and then the thing you learn from your data to get a posterior distribution. Right? So using demographics is like the prior. It's like, oh, I don't know anything about this user, just fall back on the prior. But it's really bad until you get more data. You want to get more data, you want your data-driven things to take over. I hope that answers your question. Yeah. So many people. Okay. From left. Thank you.
Okay. If you can go to your performance slide. Yeah. So here, just a quick question. With the k-means, is that distributed k-means or just k-means?
Just k-means. No, actually, it's computed in a distributed manner. Yes.
Okay.
But you just converge to very, very similar solutions anyway.
No, I'm talking about in terms of speed up here. There's very big difference.
Oh, the training was distributed, but all this speed up is just on one machine on one thread. So they're all comparing one thread. It's not, you don't compute the clusters and distribute them. Okay.
Would you recommend like rolling your own system for this, or off-the-shelf software? And if you have off-the-shelf, what would you kind of recommend for creating a system like this?
At Google, since we use C++, there's almost nothing off the shelf. And if it was off the shelf, it never worked with MapReduce anyway. So at Google, we just wrote off the shelf. At Airbnb, it's similar issues. Like I use Spark. Had this MLlib and Spark, but it doesn't do the things I want. I do a lot more complex modeling that they're not aware of. So we end up rolling out.
Hate to flog the same question that Janet raised. Could you not add additional variables as a way to fine-tune those recommendations? I know your starting point was what videos were watched, when they were watched, how many were watched together. What if you added additional variables like what devices they were watched on, what was the resolution of some of those videos? Because people would tend to watch high resolution on the bigger screens. So if you have behavioral information about what people watch on a bigger screen versus a smaller screen,
yeah,
that straight away gives you additional insight
right.
on possibly some additional insights on the recommendation as well.
Right. So this is just a retrieval algorithm. I never mentioned a ranking algorithm. So all this goes into a pool, into another algorithm above it that takes all those into account. And if you want to find out more about that algorithm, just search on Google for Google and Sybil by Tushar Chandra. And it's just, you can think of it as a massive logistic regression model that sits on top of this model and re-ranks stuff. So you could, I've tried stuff like resolution and
device form factors
and country, and they all have different different strengths. Like usually form factor doesn't really matter for some classes of videos, like chase videos,
right.
Like those Russian dashcam videos. It doesn't matter if it's blurry because people watch it because it's awesome, right? That meteorite coming from the sky, I don't care if it's 320 by 200, it's exciting. So for that class of videos, resolution doesn't matter. But for other things like GoPro, you're diving from a flight suit, those high resolution matters. So again, features in isolation are not as, they're too coarse. You want to cross them together. You want to say, given some category of video and the resolution, how do you model that? So resolution itself will give you a prior, right? Maybe people like, in general, higher res versus low res. But then for some classes, you don't care. So you want to model for low res cross Russian street videos, you want a high weight anyway because people don't really care about resolution for those. They care about the content of the video a lot more.
It could help you pre-classify some of those categories or genres, if you will, videos. Would that help?
No, it doesn't really help you. You just score them all at runtime. And you don't really know about the context of the user until the user watches something. Like there are 1 billion users and 1 billion videos. If you try to model all those ahead of time, it gets expensive. So you can factor it into user factors and video factors, and then cross them at runtime, generate a feature, and then score it. So.
You mentioned there's like a tension between exploration and exploitation, and your way of making sure you have some exploration is to add a bit of random noise. Is there anywhere where like a multi-arm bandit algorithm would fit into this naturally?
If you look at the multi-arm bandit, it looks very, very similar. So it's like e to the minus the thing. So I don't think that is the way to go. You don't know what arm you're in anyway. I do like the other method where you have the utility on the diagonal of the matrix. So what I'm doing right now is just the diagonal, right? Sorting by diagonal. But then on off diagonal, you have similarity between items. And then what you want to do is maximize the utility and minus the off diagonal terms. And I think it's called, I'm not sure what the method is called, but it's determinantal point processes. If you look that up on the internet, there's some complicated paper on how to solve that in a tractable way. And I think that's a nicer way of modeling similarity and utility at the same time. Any other questions? No other questions? Okay, no other questions. I can show you some of my current work in progress. I'm at AirBnb now, and one thing we do is model listings, and this is one cool thing that I just wrote at a hackathon. We have hackathons, so we all went to, this time it was like the Lucas Skywalker Ranch, and I wrote this in 2 days. So they didn't have anything. They did image processing, so I wrote an image processing pipeline to extract processing from images. And the left column you have like the original listing is like, and what on the right is per row is the most similar images for the listing. So you can see, okay, I got a garden here, and these are other listings with gardens. You know, like a bright light here, and these are other listings with bright lights on the right hand side. And all this can be done in like constant time using methods similar to what I talked about, like locality sensitive hash. In this case, I didn't use random projection for my hashes. I used a winner-take-all hash. If you haven't read about that, the author is Jay Yagnik at Google. And the winner-take-all hash, you permute your dense features, and then let's say the first 3 elements, you take the min of them, is related to the min hash. And then whatever token is the min, you use that as your hash code. And you just do that like 64 times, you get 64-bit hash code, and then you put it in the locality sensitive hash table, and then you can find, for a given image, like what are my nearest neighbors over a corpus of millions of listings in about constant time. And you can see, like, you know, the color sort of matters, like, you know, dark colored listings occur together, bright colored listings occur together. This is still a work in progress, but we do cool things here. That's the end, and I'll stick around with a question.
So YouTube, you're recommending digital goods, so you can always have another impression of the video. At Airbnb, you're recommending analog goods, so like the one room at that one night can only be occupied by one person.
Right.
Is there like any kind of subtleties between moving from a digital realm to an analog realm?
It's not so much digital or analog, it's the listing gets to say no. So YouTube videos can't say no, you can't watch me. But on Airbnb, the host can say, I would prefer not to host you. And in that case, it's a two-sided marketplace, right? So that makes it a lot more challenging because I can't just count anymore. I can't say this is the appropriate listing for you because the listing never changes. In this case, the host has feelings and opinions and availability and preferences. So it's a two-sided marketplace. Both the consumer, the person looking to book a place, and the person renting a place have a say in matching it up. So it's a much, much more difficult problem. It's like two moving parts. Instead of trying to figure out what people want, it's trying to figure out what people want and who want them to stay together with them. So
I have a couple of related questions, possibly. What algorithms have you implemented that are not in MLlib that you're using, and are you using those algorithms with Spark?
I've implemented a ranking loss function, which is different. MLlib, I think, has logistic regression, and I prefer something called ranking loss. In our case, there are different phases of how a user comes to Airbnb, right? First, they see an impression, Then they click on an impression, and then they ask the person about it, and then they book it. So there's several phases of how the user interacts with the site, and I want to order the phases, right? So logistic regression isn't appropriate because it's not just yes or no. It's I prefer this over this over this over this over this, and that's a ranking loss thing. So it's very similar to the ranking loss I mentioned in YouTube. So first of all, I don't know if they have that loss function. The last time I checked, MLlib is naive Bayes and logistic regression. And secondly, I'm doing a lot of sparse features in the back end. MLlib mostly deals a lot of traditional machine learning deals with dense features. I have models like these models have 16 million sparse features, right? Spark can handle that, but MLlib doesn't have the machinery to manipulate the feature transforms I want. So the feature engineering part I've extracted out into a library, its own language, like what features should interact with what other features, how to transform them. And that is custom. The solver is so easy. It's like 4 or 5 lines of code. It's like why use MLlib when I can write my own custom loss function? There's just really no point for me to use MLlib at a point.
Are you running your code on Spark though, or are you running? You are. Do you plan on merging that into Spark at all ever?
No, I used to contribute to Mahout, but I'm not a fan of the Apache patch process. It's very long-winded. At Google, it's harder because I had to get Google approval. Airbnb is a bit easier, but I'm just not very motivated to contribute it to MLlib, and I don't want to get in arguments with the contributors. I'm friends with some of them, but it's not something, there's no advantage for me to open source it. People open source things for various motivations, for fame, for fortune. There's no benefit for me because I already won an Emmy award, and this doesn't add to my fame.
You're already rich and famous.
I'm not rich, but I'm not really famous either. It's just the barrier for open source contribution for me is more than I care to contribute. If I feel like, okay, great, people are going to use my stuff, and I have an open source project called Perceptual Diff. It was for Shrek, where I would unit test images, right? All the unit tests would fail because people would count pixels and, oh, the pixels different fail. But you can't do that for movies because humans might not be able to tell the difference between 2 pixels that are different shades of blue. The human visual system is least sensitive to shades of blue. So I open source that, and I get random requests from museums that are using it. A lot of projects at Google use it to unit test like browsers and ads and maps. So yeah, that was like a interesting, good experience at open sourcing code because lots of people use it. MLlib at this point is so big and so massive, and it's just a higher barrier entry for me personally to contribute. I might open source it one of these days, but probably as a dump of the existing system rather than contributing to it. The problem, I think, with MLlib is there's a lot of contributors. If you look at the code, like the unit tests are all different, testing different things. There's no cohesion, and when you're developing some classes of machine learning, you want like an architect to make it cohesive, so various modules can talk to each other. And I don't think MLlib is appropriate for me right now to open source that kind of technology. I'd rather do it as something that runs on top of Spark. I hope that answers your question.
I wanted to understand more the questions that you're trying to solve at Airbnb. So you kind of briefly mentioned, but it seems more interesting than your short description. Like, so what type of problems are you trying to solve at
I work on search ranking. So the problems I try to solve would be how to match hosts and users so that they both be happy. But there are lots of other applications too, like how can we help hosts select better images for the listing, right? Sometimes it might upload just an image of a restroom, and they might think it's the most attractive room, but it might not be the best room that people like. So maybe we can say, try uploading a picture of your dining room or bedroom, things like that. Or sometimes they might upload pictures like this that are not well lit. And people have a preference for well lit rooms when they rent, so maybe you can suggest to them, like maybe increase the lighting in your room. They also like trust and safety issues, like maybe people put fraudulent listings. Like how do we detect people that copy and paste images and make fake listings? So there are many different applications. I happen to come from computer graphics world, so it was easy for me to switch to images. It's like one side you're generating images, the other side you're consuming them. It's still pixel is a pixel, which is not a square. There's a whole paper about pixel being not a square. But similar ideas, so it was easy for me to switch. So a lot of the things I'm doing now on images are because they didn't have anybody that could do computer vision. So it was easy for me to come up with computer vision applications.
So were you saying that you used image recognition algorithms to actually make those recommendations to owners that you should change the image?
No, that's one of the possible applications. I haven't done that yet. So. Although this morning, live on the site, there is an experiment that tries out these image features so that things that are better looking have a small boost to the scores.
Yeah, but you could have, that allows you to extract certain rules from the images that says, these types of images lend themselves more likely to be rented.
Yeah. So I actually do compute that. Yeah.
Okay.
Your question?
Could you just briefly explain how you managed to write that algorithm for the photo?
Sure. It was an easy thing for me to do because I've done it before on image search and YouTube. I compute a bunch of different histograms for the features. Like for this image, I'll calculate what is the green distribution or whatever. And those are called red, green, and blue histograms. I compute that as one histogram and color histogram. Then the other color space that is common to use is hue, saturation, value, HSV color wheels. If you're familiar with them, those color wheels, they convert the color space into something that is the angle is the color, and then how close to the center or how far away is how saturated the color is. Saturation being like dark red versus pastels or something. And then value is how bright or dark it is. In the HSV space, I throw away most of the value. It's more like what does the color look like. That's another histogram. Then another histogram is like shape, like what kind of, are there diagonal lines here, are there vertical lines, horizontal lines, and put that in a different histogram. And the last one is like texture, what kind of patterns are in this. So if you just look up on the internet your favorite feature extractors, you'll find these. Then I have 4 histograms, I concatenate them together. Actually no, I compute a hashing on each histogram separately. I compute like 32 tokens or something per histogram. And then I concatenate that to one giant hash code. And then I make an inverted hash table. So I'll have maybe 128 hash codes per image, right? You can think of images, these hash codes as words. So an image will have this bag of words. And so I make an inverted hash map that goes from the code to an image. And then so for a brand new image like this, I'll say, what are the words you have? It gives me 128 words back. Then I look up on the table all the possible images that contain at least one of these words. So then I get a candidate set of maybe 10,000 images. And then among those 10,000 images, you can compute the dot product distance between the hash codes, right? How many, the intersection basically. How many of these hash codes intersect with the other image and the one that has the most wins. And that's the sim here. It's like the number of hash codes in common. I'm not sure why it's a floating point number. It should be an integer. Yeah, I'm not sure what I did. I might have done some funny normalization. I might have done TF-IDF in this experiment. Are you familiar with that? The term frequency inverse document frequency weighting. So that's a information retrieval thing. like the occurs in every web page, so it probably should have weight 0, right? And then something unique, like the word unique, should have a high weight because it occurs so rarely. And that's one benefit of like switching different fields very rapidly, is you get ideas from different fields, right? I got ideas from working in games. Like all my optimization skills come from working in games, in movies, and then all my image stuff come from working on images, and then all my skills on learning how to personalize stuff come from YouTube. So it's kind of fun, like if you're in a big organization, try to switch from role to role to role, because you learn a lot of different things, and then you don't lose anything from the previous role. You learn something new, and so that's what I've been trying to do. I try to go to a role where I learn something new and exciting, and that helps a lot. Unsolicited advice was asked for. Any other questions?
Thank you.
Well, thank you very much.